Okay, so should we start? I think we have everybody, right? Okay. So any questions in the last class about what we went through? Any questions from the last class? Yes. So I'm just waiting for Paul to make some logistics, and then I can give you, I mean, basically he has to note down a few things and then he can give it back to you. Okay. Okay, so today we're going to go over a new concept, chemical shift imaging. Well, I think you were actually briefly introduced to that in one of the discussion classes, I think. And then we'll just go a bit more into the details in terms of specifically for fat imaging, how we can use that chemical shift property. Well, just a quick recap. So you went through the contrast concepts last class. So long TR short T is spin density weighting, short TR short T is your T1 weighting, and then long TR long T is your T2 weighting. And we looked at the effect of contrast agents, and then we saw that it's useful to look at vasculature. It enhances T1 property, but it also does T2 property, and the what property you're sensitive to is a function of your imaging sequence parameters. And then we looked at how contrast noise ratio and resolution are related, excuse me, which is actually a byproduct of the noise properties in terms of how many samples you collect would change your noise in your data. And then we looked at partial volume effects, how they're useful in some of the cases. These are a few examples we went through. And then this is the chemical shift part that we're actually going to go over today. And the left plot that we see would be, we'll go over a bit into the details of that plot, essentially what that is plotting. So the key points that we're going to cover today is chemical shift property and imaging, and then the fat water shift. I think I mistyped, it should be fat / water shift, and then imaging fat versus water fraction in the tissue. So chemical shift is, well, we've gone through earlier that different nuclei have different Lamer frequencies, right, owing to the gamma value, right? Different nuclei would have different gamma value. So similarly, another property that is observed is for the same type of nuclei, for example hydrogen nuclei, for different chemical environments and chemical structures, the protons in those materials, for example alcohol, lipids being fat, triglycerides basically, and then water. So all of them have hydrogen protons, right? So, and you can image hydrogen protons because the gamma value for that hydrogen proton is the same. So, but owing to the chemical environment, the microscopic molecular environment within which that particular hydrogen resides, there is a slight shift in the resonance frequency that proton experiences, and that is understood to be a function of the electron cloud around that nucleus, and it's called a shielding effect of that particular electron cloud. So that's as far as I can go in terms of explaining the source of chemical shift, where it's coming from. But what it manifests in as far as we are concerned when we are doing an NMR experiment or MR imaging experiment, is that it manifests is the finite frequency shift that particular proton experiences with relation to the Lamer frequency that it's supposed to experience. So if gamma times B naught is the Lamer frequency that the proton is supposed to experience, but the frequency experienced by that particular proton due to this shielding effect is shifted by a particular fraction. So that shift property is what is called the chemical shift. It turns out it's proportional to the B naught applied field. And if you, for example, if your sample has a spread of these chemical shift properties in the nuclei, then your signal would be basically sum of those different resonant frequencies of those nuclei. So that's what that particular first summation is talking about when you do an FID experiment. The point that I mentioned about different gamma values for different protons is also similar in nature, provided you are able to excite all these protons, because your excitation frequency, if it includes these sodium and phosphorus, which means it's a quite wide band RF pulse that you would have to use, then the situation is similar. Basically, different resonance frequencies, the signal that you would get is the summation of all those frequencies. But here we're talking about much smaller differences between the precession frequencies of these nuclei, and all of them being hydrogen protons. So if you observe, it's similar to this equation where we are writing the difference in the resonance frequency of the protons is similar to writing a change in frequency which can be a gradient, which can be due to a gradient, or which can be due to an unwanted background field inhomogeneity. So the mathematics works out to be the same when you integrate that signal. It's just that this is more this is a material property which is fixed compared to a magnetic field inhomogeneity which is spatially varying. It is or a gradient which you are applying and which is linear in nature. So it's just the nature of that delta B term changes when you're writing this equation. So chemical shift property can be written in this form, where the experienced field is written as B naught minus the sigma, which is basically the chemical shift which characterizes the chemical shift property, and is proportional to B naught. So B naught minus sigma B naught. So that is the net field experienced by the proton, and if you jump into the rotating reference frame, so the B naught is gone, and all you have is the shift related to the center frequency, which is sigma B naught. Everybody follow that, right? Sigma is the chemical shift property, which is measured in terms of the ratio of the experienced field divided by the applied field difference. Actually, it's basically this minus B naught divided by B naught, which is basically the difference in the resonance frequency of that particular proton divided by the applied magnetic field strength. It's not resonance frequency, it's the difference in the field divided by the applied field. So it's delta B divided by B. Where's this? B shifted is B naught minus sigma B naught, right? So delta B divided by B naught is sigma, or actually minus sigma in this case. So that's B shifted minus B naught divided by B naught. Or if you just write sigma, that's relative to the applied field, it's B naught minus the B experienced by the nuclei divided by B naught is your sigma. So that is why it is unitless. So it's expressed in parts per million, because that's the order of that is the order of magnitude for that particular phenomenon that we observe.
Parts per million is the difference compared to the applied field.
So this is parts per million.
Right.
Right. So the difference in frequency can be in few megahertz or few hertz. Not megahertz, sorry, hertz, few hertz. So that is how we express the chemical shift for a given particular proton. So as you can imagine, as I said, this is a function of the chemical structure of the particular chemical or tissue which contains that particular type of material. So lipids which contain triglycerides have quite a few CH2, CH3 molecules, and neurotransmitters have different hydrogen proton. I don't know exactly what molecule it has, but it has hydrogen protons which also have a quite finite chemical shift related to the surrounding water. And remember, this is all relative to the center frequency for hydrogen proton, which is taken as with reference to water. So gamma B naught, where gamma is for the hydrogen proton, that particular resonance frequency is for pure water, and that's what we are taking reference as in this case as we speak here. But in for example, chemical shift for for fat in general, there is a spread of chemical shift frequencies observed for protons in fat, but the mean chemical shift frequency, if you express that in frequencies, you would have to multiply this 3.35 parts per million with B naught, but the mean chemical shift is observed to be 3.35 parts per million. Okay, but this is relative to water. In general, in NMR, it's one of the other standard chemical species called tetramethylsilane, or I think TMS is the acronym for that. So that's what is used as the reference for relative to which any shift is being observed. In fact, relative to that, I think water is slightly paramagnetic, meaning it's experiencing slightly higher field strength compared to TMS. But nevertheless, in our context, we are referring to this chemical shift relative to mostly water whenever we talk about the chemical shift aspect. And that's because when you are doing an imaging experiment, let's say you put a sample in the magnet and you want to start your experiment. Now the transmitter, RF transmitter, and the receiver has to adjust their gain depending on how much volume of signal they would expect. I mean, how much amplitude of the EMF that they would expect from your volume, correct? Everybody following me on that? So initially, without even before doing actually your experiment, the spectrometer sends in an RF pulse of a large bandwidth and then tips it and then receives the signal and then looks at the frequency spectrum of that signal, of the FID, and then says and converts that to the frequency domain and then looks at the center frequency relative to the transmit frequency that it transmitted, the spread of the frequencies, and then the peak, wherever that peak occurs in that frequency axis, that's where the spectrometer's transmit frequency is going to be centered when you are doing the next subsequent experiment. So let's say your sample has quite a bit of fat and very less water or water protons as such separately as a water entity, meaning a water compartment, let's say. So let's say you have pure fat and pure water compartments, but the water compartment is very small compared to the fat compartment. So obviously when it does this testing initially, it would shift the center frequency to fat. So in our experiment, in our general imaging experiments, because we have a lot of water, everything is centered towards water when we are doing the imaging. So whatever shift we are calculating is always related to that resonance frequency of water. Is that clear to everybody? Okay.
Can you say it again how we actually select or choose that central frequency?
So imagine just this experiment where you are applying a 90-degree pulse. I'm not sure exactly what degree of pulse, meaning what flip angle that this spectrometer uses, but let's say you are using a 90-degree pulse experiment and you just applied a wide bandwidth 90-degree pulse, and in the hope that you will be exciting whatever resonance frequencies are there within your sample, and then you will have the same bandwidth for your receiving. You Fourier transform that FID, and then you would basically see where the center frequency is, meaning that you would get the Fourier transform and then see where the peak is occurring relative, and now this is relative to your Larmor frequency, right? Because whatever RF bandwidth, RF pulse you are applying is centered around the Larmor frequency of hydrogen proton, and you are defining a bandwidth around it. Then you are applying, you don't know what the sample contains. The spectrometer doesn't know what it's imaging, right? So it doesn't know the center frequency, what it should be using for optimal excitation. So that's when you use this, that's how the system determines the center frequency. If you observe, if you go back and possibly look at, well, for humans probably it won't change the center frequency much, but if you put two completely different phantoms and observe the after you do the experiment, you observe the center frequency that was used for your imaging experiment, you can see the shift. Okay. So this is one example where you have a completely fat phantom meaning a jar of a bottle just containing pure triglyceride oil plus some water, some amount of water just to give a contrast, and then you put it in the center in the magnet and then try to do the imaging, and you would see that the center frequency is going to be shifted towards the larger peak, which is going to be here, fat.
Does it happen all the time?
Yes, any experiment. No, any experiment that you're doing. Any, I'm not quite sure in MR how these spectrometers work, but definitely in MR imaging experiments, you would observe that happening right before the experiment is being implemented. Okay, so let's come back. So MRS is basically spectroscopy, which is well, you're looking at the spectrum anyway. You're doing that already. In this case, what distinguishes it is that you're not trying to quantify the spatial distribution of it. You're just trying to quantify how much of it is there. So in a sample, you excite. Well, let's take the previous example. You have fat and water. So you want to quantify, and let's say they are both mixed. Okay, so mayonnaise is a good example, I guess. Right, so it has some water, it has quite a bit of fat. Right, so you put mayonnaise in the scanner and then try to evaluate how much fat is there and how much water is there. You can do that experiment basically just by exciting the so let's assume it just has two center frequencies. One is centered around 3.35 ppm relative to water, and then let's do this experiment where you excite the sample and then you get the FID without applying any gradients, and you do your Fourier transformation. Everybody following me on that, right? So then now all you have, whatever difference in the FID would decay because of the difference in frequencies of these two fat and water components, right? It will become e power I, so it will just be, you will see later on that the equation would just become rho of water and then rho of fat, which is precessing, which has this additional sigma p naught gamma t frequency. Everybody got that? How we get that? So this is fat, sorry, this is water that you're imaging normally, and you're not doing any imaging in this case. You're not applying any field gradients. It's just the spin density that you're going to get, right? Assume that it's uniform magnetic field. The applied field is absolutely uniform. There is no other delta B, source of delta B. Then what you would get is just this center peak, right? Which is resonating at Larmor frequency. And then you would have this which is resonating slightly at a different frequency. Okay, we'll come back to that expression. The point I was trying to make is that once you take the Fourier transformation of that FID, all you get is two peaks, one corresponding to the center frequency of water, one corresponding to the center frequency of the fat. Can everybody see that happening? Okay.
So your reference frequency will be according to the fat one, right?
Well, if you have for more fat, right. But in plotting, of course, you know the center frequency of water, so you can plot it relative to water. But it's the amplitudes that you're interested in, as well as the shift, both, as well as the relative shift, relative to one another, exactly. And then once you know your center frequency, let's say you want to shift that to relative to water, then you can always center that relative to water. You can plot what the shift in the spectrum relative to that as your center point. So we'll also be discussing briefly this aspect of magnetic resonance. So that part is called the spectroscopy, where you're getting the spectrum of the chemicals that have these distinct chemical shifts relative to the center frequency or relative to your water. And the peak is, or the area under the peak is corresponding to the volume of that particular sample of that particular chemical. So that is spectroscopy. And MRSI, which is spectroscopic imaging, actually does one more additional step, which actually does the spatial encoding and then gets spectra at a particular location within your sample. So how we are doing that, we can, I think, well, actually we did discuss that briefly when we were discussing K-space, and I think you will be reminded of that today, and we'll go one step further in that. So this is what a typical spectra looks like. In the brain, we have these different chemicals whose chemical shift is big enough relative to the center frequency that you can actually detect those: N-acetyl aspartate, creatinine, choline, inositol, and then lipids, of course, and then lactate. So lactate, just for your interest, is lactate is important when you have anaerobic metabolism. You will have lactate buildup in your body, in your tissue basically, so you want to kind of identify the presence of it when there is anaerobic metabolism and potential tissue damage. So just like the imaging scenario, if to increase the signal to noise ratio, you want to average your measurements. If your signal to noise ratio is low, and again the same dependencies of the voxel volume, signal and voxel volume, apply to this as well. It's similar NMR experiment, except for that you're not doing a imaging gradient. You're not applying imaging gradient. That's all. So without applying the imaging gradient, you're acquiring your FID or the echo, and you're doing a one-dimensional Fourier transformation. It will become clearer once we look at the sequence diagram.
So why the duration of the ppm axis is from right to left?
That's essentially convention. It's typically convention, that's all. So it's plotted 0 here and then this on the towards the left.
The water.
Right.
And it's not shown here, so it is like a water surface.
Right. So I mean, if water peak is quite big compared to this, so if you show the water peak, then you can't see this, because the scale, of course, is order of magnitude larger. So which is why you won't be able to see these peaks. No, there is no, well, we haven't, well, in this case, the example that I'm showing has some encoding. We'll come to that, how that is being acquired, but even if you just do the whole brain, let's say, then you would still see similar spectra.
So red one is the fitting?
Right, so once you get the spectra, you try to quantify the area under the curve. Of course, just like any other measurement, it has noise. So you want to discard noise when you're trying to acquire or quantify the area under that curve. So for being able to do that, you use a curve fitting approach to fit the peaks and then get the area under that particular peak.
So the baseline thing is corresponding to, relative to what? If you are quantifying the area under the peak, so till what point, what is the baseline?
Well, if you don't have any other sources of phase or B naught that would affect your baseline, then it should just be flat, just like your image. In your image, do you see any baseline shift when you do the Fourier transformation? No. So, well, that's because you're taking the magnitude of it. It's the same case here. But it is affected by phase abnormalities when you have background field inhomogeneities, which would affect your baseline in this case. So there are certain algorithms to process and make sure there is no baseline error. So to correct that, there are other fitting procedures to remove the baseline error or baseline bias, basically, which could be overriding your spectrum. So in this case, this is the baseline corrected spectrum where you have no bias due to external background field inhomogeneities. And like I said, it's one second. So like I said, it's the relative peak amplitudes that we're interested in this case. In some cases, we are also interested in the absolute peak volumes. There you have to be extra careful when you want to do the baseline correction to make sure that it doesn't introduce any additional bias in your area calculation under the peak.
So when we are quantifying the area under, suppose this N-acetyl aspartate, so we include that small jiggles or around that. So that is also.
I am not an expert on that, but typically that's not the case. If you want to look at the ideal sample which has all these peaks, it should just be something like that. That's my understanding, but I'm not sure what other sources of resonances or chemical shifts that you would find between Na and creatinine. This is at 3T, I believe. Yeah. And as you can imagine, if you look at the previous expression, the resonance frequency shift is proportional to this sigma times B naught. So the higher the B naught, the higher is the frequency shift. This ppm scale doesn't change. Everybody with me on this? So the chemical shift is not changing as a function of field strength. That is always the same. The x-axis is always the same. Whereas your sensitivity to be able to pick that difference up at let's say at 1.5 T, the difference in frequencies due to two chemicals is only 10 Hertz, or let's say 50 Hertz. 50 Hertz difference is difficult to pick up compared to a 100 Hertz difference, which you would see when you go to 3T, or when you go to 7T, that becomes even larger, right? More than 200 Hertz, right? So that's when you can start seeing peaks of smaller molecules which have chemical shift somewhere in between. But when you don't have that sensitivity, then you would start seeing you would just see some noise because you don't have the sensitivity to pick that up. Is that clear? So MR spectroscopic imaging is also called chemical shift imaging. That's another name for that. And there are different ways of doing it. We are going to go over maybe one example of it, and then we'll shift gears towards imaging aspect, which is what this whole course is about, which is and within imaging, we will be talking about how to image fat and water based on the chemical shift property, for using the chemical shift property. Okay, so MR spectroscopic imaging, we can do that by, let's see, I think I have this sequence diagram. Yeah, okay. We can do that basically in 2D, 1D, or 3D, meaning the spatial encoding can be 3D, and then the chemical shift encoding forms the other dimension. So if you're doing a 2D imaging experiment and 1D chemical shift imaging experiment, or a chemical shift spectroscopic experiment, then that one becomes the third dimension, so that's 3D. And if you are doing 3D spatial encoding, that one dimension would add and just be 4D. Let's just look at the sequence diagram, and then we'll be able to understand this a bit better. Now in this case we are showing a spin echo variant of it. You could also do an FID variant of it, basically by just applying your gradients, encoding gradients, and then getting the FID. But spin echo, as you know, helps us to get the center of k-space better compared to an FID, so that's usually preferred. So let's look at this, and can anybody explain me what's happening there? Anybody venture? I mean, it's self-explanatory now that you have understood how to read these sequence diagrams, right?
So basically we're giving 90-degree pulse, and simultaneously we are...
Do you want to come down and draw me the k-space diagram for the 2D? I think that will be easier.
So both are zeros, then negative, so
That's okay, that's fine. It doesn't have to be perfect. Okay.
So it will come here, then we apply 180 degrees, so it will go here. And then plus
then what's happening? We're not doing it, well, we are doing an imaging experiment, yes, but remember, so you're sampling the echo, sampling the data around that spin echo, right? There is no imaging gradient on, right? So basically you're just stuck at that point, and then you're going to get your echo. So what does that echo have? What information does that echo have? Okay, you can go back and sit. So next data point, let's say, so you're sampling, if you're just drawing up the matrix, what data you're collecting, so this is your echo along this direction, right? Okay, so the next data point, let's say you're going to this one, and then you have this echo here. You stored your echo. Okay, so what does this echo, what information does that echo have? So your typical imaging, ignoring the relaxation effects, S of t, or you can write that as S of k, let's say, is integral, let's try one dimension first, dx. Anybody? This is along x direction, so right? Okay, now so rho x now has here we just assume that there is no other background field inhomogeneity except for the imaging gradients that you have, that you applied. Now we have this rho or being summation of rho I e power I sigma I. Sorry, well, yeah, rho I is your spin density for that particular chemical species, B naught times gamma times T. Everybody with me on that, right? So you have that. So this integral would transform to S of k, even though sigma I is also a function of space, but essentially you are not trying to encode that part yet here. You're just trying to encode everybody can see this or no? Oh, okay. Try to write it here then. Okay, so here you can read it, right? Okay. So S of k is sigma dx, sigma over the chemical shift well, this is a continuous scale, so we don't have that. So it's actually, well, yeah, so you can use the minus sign here, and then that is everybody with me on that, right? Everybody understands that? So this integral is kind of implicit. We don't particularly write that, but it's integrating over the finite chemical shift species that you have within your sample. Okay. Now we're back to the previous case where you had this e power mod t by t2, and then you're changing this t into t prime into write that in terms of k. Right. So the same expression, same exercise. You do that. And you end up with an expression which we'll write in a minute. So let's do that here. S of k now this is basically t is t prime, well, t prime is t minus te, correct? And t prime is gamma bar g, sorry, yeah, divided by k. Is that right? No. Hold on, sorry. K is gamma bar g t prime. Right, so you can go substitute that here. And you want to substitute for t here. So basically we have t prime plus te translates to k by gamma bar g plus te, this whole thing times gamma times p naught times sigma. So what you end up with, so this whole thing, so what you end up with is in the exponent. Okay. So this is additional linear phase. This is a constant phase term because it's t is a constant, right, for your experiment. Nothing else is changing there except here you have the variable k. So that is a linear additional phase term, which if you recall your phase or shift property of your Fourier transform, so if you have phase in the k space, linearly varying phase in your k-space, then that would lead to shift in your image domain. And if you have a linearly varying phase in the image domain, it would lead to shift in the k-space domain, right? Okay, so you will see that effect in the coming slides. Now, the whole point of this exercise is that you are basically doing Fourier transformation along this time domain. So once you acquire this sample, you're doing Fourier transformation along the time domain, and that Fourier transformation is going to give you a spectrum like this. Without the Fourier transform, the image looks like that, where each location has this particular spectrum. Everybody following me on this, right? Remember, you did this exercise at one point when you're if you just sample the center part here, let's just say you just sample the center part here, where the phase is 0, meaning phase due to the spin echo part, whatever phase encoding you have done along the x and y direction, that is always going to be there, okay? But the phase at the center of the echo for that particular spin echo is going to be 0, right? Now, which means you traversed for the first part, you did the phase encoding and you went to here, and then 180 pulse ended up here, and you get this sample, and then repeat the same experiment for a different combination of phase encoding along x and y, you get this sample, so on and so forth. This is the most inefficient way of collecting your k-space, correct? So you're doing that, but you're doing that here because of the additional benefit that you're not just sampling the center, you're sampling the whole around the echo, and then doing for a 1D Fourier transformation to get your spectral information. You understand that now? Okay. So once you kind of take that spectrum along the one dimension and then do the Fourier transformation, then you would get these peaks, which is what you're interested in. Well, in this, which is what you would get here, something like that. So this is what that experiment did. And this expression, let's come back to this. This is nothing but, written in three-dimensional mode, whereas here we just saw the one-dimensional example. Okay, so essentially you're using phase encoding to go through your k-space, then using your spin echo to acquire the center of the echo, and you're doing the 1D Fourier transformation to get your spectral information. So this is basically your chemical shift imaging, or CSI, not the TV CSI but MR CSI. I don't know if anybody caught that. Okay, good. Okay, so basically, again, if you go back and now look at the imaging time for a 2D CSI experiment, that's going to be the number of along the spatial dimension nx and ny points that you are collecting, and along that, because you're sampling this, so this is like your nx in your typical 3D experiment, this is like your nx. So this is also 3D k-space, isn't it? This is also 3D k-space, except for the fact that this third dimension is time domain, spectral information rather than spatial information. That's all. So the imaging time is nx times ny times tr, and if you're doing averaging, that's n acquisitions. Because you're doing phase encoding, you don't need, and you're not applying any gradients while you're reading out the echo, so there is minimal bandwidth requirements for such an experiment. Because if you can imagine, you can do phase encoding in two ways, right? You can either keep this duration constant and then increase your gradient strength, or keep on increasing your keep the gradient strength same and keep on increasing your time that you apply the gradient. Either way, you can traverse the same k-space line. Of course, you can think of advantages and disadvantages for that, because every time you're increasing your phase encoding gradient duration, then you'd have to shift your TE or use a longer T so that you can accommodate all your encodings. If you're just shifting, keeping gradient staying constant and then shifting, expanding the gradient lobe. So each has its own advantages. And these we are assuming that there is no at this point we didn't have any T1 and T2 decay parts included in our experiments, but you'd have to consider that as well when you're practically doing an imaging experiment. I mean, when you're practically doing a CSI experiment. And for just like the imaging experiment, the signal amplitude is proportional to your voxel volume. So to get enough to be able to reconstruct your enough signal to noise ratio to be able to reconstruct reliably this spectrum, you typically average this acquisition a number of times, 64, 128 times, etc. On the other hand, instead of actually dividing up your volume like this, you're just imaging this whole volume, then you would have a lot of signal. Then you don't have to average as many times. You get the point, right? Okay. But as you can see, this such a spectroscopic imaging experiment requires quite high homogeneity, because in this equation you're assuming that except for the imaging gradients and your chemical shift, nothing else is influencing your magnetic field that the protons are experiencing. So if you have a magnetic field spatial gradient due to, let's say, susceptibility effects or sinuses, so same thing. So sinuses meaning air has large susceptibility difference relative to water, so it leads to quite a bit of 1 by r cube decay of the field perturbation, basically, meaning the field is not going to be B naught, but it's going to be spatially varying around the sinuses. Let's say this is your mouth, and then this is your brain. That's pretty bad drawing, but just go with me on this. So your field typically here around the sinuses goes down like that. So this is your B naught. It can also go like that, 1 by r cube, doesn't matter. It can be lower or higher. So because of this variation, it's typically difficult to do spectroscopy here, because you need to be able to make sure that your homogeneity is pretty good, meaning ideally flat, the B naught field, applied B naught field being flat. But if it's not, then it's going to affect you, which is why you have what is called shimming. It's a tool where you're able to modify the you're able to basically smooth out this particular variation within the volume of interest. Well, how that happens is a whole different discussion that we would have to either postpone to a next session or maybe in the review session, let's say. But there are tools available to be able to some extent homogenize the field if you have just a linear or quadratic field variation in your volume. Okay. So we have already gone through these points where acquisition time is that, and if you're doing 3D spectroscopic imaging experiment, then you should be very patient, or you should be imaging an animal or some non-moving object, which you can image for like 2 hours, 3 hours overnight or whatever, basically. So it takes, bottom line, it takes a long time for you to collect that data. Field homogeneity requirements is quite clear to us already. So now we're shifting gears. That's the extent of spectroscopic imaging and spectroscopy that we are going to be covering. And then now you have to understand now that just like the Nyquist relation that you have for sampling, you would have similar relationships for your sampling constraint. That puts a constraint on your sampling rate for your spectroscopic imaging. Okay, so just think of that, and well, you can think of that very easily in terms, if you think of your experiment in terms of your bandwidth of your signal that you're receiving. If you know the bandwidth, then you can determine your sampling rate, which is well, you can go back to your book and go back. Actually, in the textbook, I don't think that point is covered, but you can come up with that requirement just by following that. Basically, if your bandwidth, so this is minus omega and then this is plus omega, you know these, which are a function of your sigma. Then if your bandwidth is 2 omega, well, in this case this, then your sampling rate is basically that divided by 2 pi. Well, please don't, well, I hope this is already clear to you guys. This is what we followed in Nyquist sampling, right? Okay, good. So, and that will govern your sampling rate, etc. For your spectroscopy experiments. So let's come back to your to our imaging domain, which is what we want to we're focusing on in this course, and look at fat, which is quite a lot depending on the makeup of the person. I mean, constitution of the person. You either have a lot of fat or medium fat or whatever, basically. But basically, the bottom line is you have fat in your body, and fat has a chemical shift of 3.35 ppm, and it essentially means that this is the equation of signal that you are getting essentially when you're doing your imaging experiment. So, which in other words means that, well, I guess this is not, I think we should have written this whole thing clearly again. Let me just write that so that it's easy for future discussion. Minus this whole thing. Oh, sure, I removed that, but that's okay. I think I remember that. Oh, there's no gamma here, sorry. It's already. So same thing, so minus I. Okay, so this is your signal expression when you have fat and water within your sample. And this spin density is essentially, it's the combined average spin density of your fat and water. It's not making a distinction between fat and water. If you have a voxel which has both fat and water, that's the signal that you're getting, where rho x represents the total spin density of your voxel, yeah. But you can, in principle, separate the water expression, which only is subjected to this, and then write the fat fraction as rho fat. Again, the imaging component, the same imaging component would continue, and then this would be your additional phase that you would have for your fat fraction. Is that clear to you guys? Okay. So the point I would like to draw your attention to is this additional phase term, which is constant, and this linear phase term, which is going to induce a shift in the imaging domain. So both are referred to as chemical shift artifacts. Well, chemical shift effects, whether they are artifacts or useful, that depends on the experiment that you're designing. Okay, so basically, if you have a partial volume voxel which has both fat and water, then you have a scenario where fat is having this additional terms of linear phase as well as this constant phase, whereas water doesn't. So these two would have, and it's the summation that you're getting in your that you're obtaining in your signal acquisition. So that summation is basically your vector summation of these two phase terms, these two signal terms, and that leads to a few effects that we will see in the next few slides. But one effect is clear, is the shift effect, where you have a linear phase shift due to the fat fraction, and that fat fraction, because of this linear phase shift, is shifts relative to water in your imaging experiment. Everybody following me in that? Okay, so that shift would become apparent to you. If we write this expression, so if we just carry on writing this expression in a slightly different manner, so this x, this is the mapping that you're doing. Instead of mapping x, you're mapping x minus this sigma b naught by g readout. So that's your absolute shift in fat when you're doing the imaging. So fat would not stay where it is when you're doing your imaging, but would shift by that value. Now, as you can imagine, if you have a really large readout gradient, then this term can go to 0. Can everybody see this? Okay, good. So this term of here again. So if your readout gradient is very large, then this can go to close to 0, and there will be minimal shift of fat. There will always be some shift. There will be minimal shift of fat if you use a very large readout gradient. Now, if you write this in terms of the number of voxels, then it's basically okay. Is this appropriate to write? This is x, sorry, my handwriting, yeah. So in terms of your finite voxel size, delta x, if you take that out commons, and then that appears in the denominator. Now, so this is the physical distance that you would move divided by the voxel dimension. That gives you a number of voxels that it would shift. Or if you can write this in other words, if you multiply both of them with gamma bar, so this is nothing but your read bandwidth per unit voxel, gamma bar gr times delta x. So just multiply this with gamma bar. And this is your fat water shift in hertz, and this is your read bandwidth in hertz per pixel. Okay, let me write that again. Everybody has question mark faces on their, expressions on their faces. So everybody is clear until this point of how we got there, right? It's from that expression where if we take I2 pi kx common out, then you see that x is shifted by this much amount. So when you write this in terms of finite voxel size, that is basically The G sub R basically is readout gradient, right? No, actually there is delta x here because you've taken out. Okay, so if you multiply both up and down, just this part, I'm just trying to see, characterize this shift. So that's basically gamma bar sigma b naught divided by read bandwidth per unit voxel per pixel basically. So that's gamma bar times delta x times gr, right? Okay, so this is in hertz per pixel. This is the delta f sigma, that's chemical shift in hertz. So this is hertz. So you would get basically the number of pixel shift using this expression where delta f divided by your bandwidth read per pixel. Everybody follow that again? So in fact this is a parameter that you would see on your scanner when you do your any imaging experiment and you go and try to change your bandwidth. The system typically Siemens would tell you, but Philips or GE might also have some other mode of conveying that message to you guys, to the user I mean, where you would see that this particular bandwidth implies how many voxel shift of fat. Because remember, for a given for a given field strength, the fat shift ppm is constant, right? So based on that, they can calculate, okay, for this bandwidth, for this read bandwidth, this part I know this is constant. For this particular read bandwidth, how many voxels of shift am I going to see in the data collected? And once you know that, you can adjust your read gradient to whatever acceptable level you have for your imaging experiment, and then use that. Now if you have a voxel which contains both water and fat, then this additional phase term is going to cause the fat is going to shift, of course, and within the location where it shifts, again within that location most likely there will be water as well. So when you're trying to image that, and let's assume that, let's say by optimizing your experiment you're able to have very large bandwidth so that your shift in voxel is only 0.5 or 1 voxel, well less than 1 basically. So under that scenario you have fat and water within a given voxel, then the fat component will have this additional phase term, whereas water will not. So because of that, you will have this phenomenon where if these are the spins of fat and water, so relative to water, the fat part will have a phase which is a function of time, or which is a function of TE basically. That's TE, right? So depending on your TE, you may have these two vectors in sync, or you may have the water and fat like this within that voxel. So if you have a partial voluming effect, then these would just cancel out and your net signal is going to be diminished or enhanced depending on which situation you're in. So these are the two effects that we're going to talk about further, but for various other reasons, and quite a few disease conditions, it's important to actually be able to image fat separately and water separately, or look at the amount of fat content in the body, or sometimes suppress the fat signal so that you can actually look at the other tissue more easily. For example, if you're using a body coil, then the tissue which is closest to the body coil will have a lot of signal, and typically whichever part of the body you put your coil on, usually you have the subcutaneous fat, which is the closest to your body, closest to your coil, so that would have the largest signal intensity. So to avoid that obscuring the other imaging features within the F field of view, it is of interest, it is beneficial to actually suppress the fat signal and then do your imaging experiment. So in those situations, so either selectively imaging, being able to image fat, or selectively imaging water, or quantifying fat water fractions, or selectively nulling either water or fat, all of these essentially boil down to the fact that whether you are able to distinguish fat from water, what properties can you use. One of them, of course, is chemical shift. The other one we have already looked at, where the T2 and T1 properties, based on which you can generate contrast between those two tissues. And T1 is especially beneficial for us in the sense that you can do an inversion recovery experiment to null the signal from fat. So that is one of the ways actually implemented that to be able to see the other tissue much more clearly compared to without the fat obscuring your ability to distinguish those features. So inversion recovery is one way of doing such an experiment. We'll come to that, but let's look at how well, this is basically reiterating what we had just discussed in terms of how fat shift affects our imaging experiment. So you have the number of voxels shift due to the presence of fat being given as this, which is what we had here, which is your fat shift in hertz, and then this is your read bandwidth per unit voxel. At 1.5T, this is 214 hertz for the average chemical shift frequency for fat, and if you do the read bandwidth, or the bandwidth along a given direction in your experiment, along the read direction is this, which we know is this expression we've already gone through. This can be written as this 1 by Ts, and in the phase encoding direction, because you're taking much longer basically, so this is much smaller, the bandwidth along the read along the phase encoding direction. But you have to that is in EPI basically. So this is not in the conventional imaging. Conventional imaging case, for the you're encoding the y direction every step, and there is no phase accumulation along the y direction when the phase for a given so if you have two data points along the y direction, right, as a function of x, the phase at this point and this point is always the same. As a function of y, you are changing that, which is what is your encoding, right? As a function of x, the phase here and here is same along the x direction. So because of that, you won't have any distortion in the conventional imaging case, but in the EPI, which is ecoplanar imaging, it's a different mode of acquisition there, where that part is violated, which is why in that case the bandwidth along the y direction also comes into play, and that also becomes important when you talk about fat shift. In the conventional sense, along the y direction, that particular phase accumulation doesn't happen, so that part does not even appear. So this is an example where you have fat. This is a phantom that I was talking about. If you have fat and water, let's say in this case both the volumes, let's say water is higher, so let's make our you can see this is fat and this is water. Water is the center frequency is actually centered around water because the volume is higher. And if you do an imaging experiment with very low bandwidth, then you would see this shift, and this shift how many pixels this should shift can be actually predetermined even without doing the experiment, because this is an experimental parameter that you're setting, and this is a fixed parameter for the given fat or given chemical species. So you can actually predetermine how much of a shift that is going to occur in the experiment. So this is the same derivation that we saw here, and this is the illustration from the book, where if you have this particular spin density distribution and you're trying to do imaging using low bandwidth, then the fat would shift and it will cause a spin density distribution, something like that, which is what you're seeing here. Now comes the cancellation part, which we introduced here. So you can write, if a voxel contains both fat and water, and you can write that equation as relative to water, fat has this particular frequency phase as additional phase term, which is dependent on TE. So for a given TE, fat will have an additional phase. Okay, and now if you time your TE based on this particular parameter, which is a constant, which is known, if you time your TE appropriately, then you can either have this term as 2 pi, meaning these two are in phase, or 2n plus 1 pi, meaning that these two are out of phase. In phase, out of phase, vectorially added. So this would be basically rho water plus rho fat if you have 2n pi, or if you have 2n plus 1 pi, that will be rho water minus rho fat. Everybody follow that? So this is basically, this is becoming pi in this case, I mean effectively, because of the periodicity of cos and sine, and this is becoming 2 pi in this case. So now imagine if it's pi by 2, what would you have? So that would be rho water plus rho fat into cos of pi by 2, which is 0, plus I sine pi by 2, which is 1. So basically it will be rho water plus I rho fat. So if your field was perfectly uniform and you did this experiment choosing your TE such that your phase for fat was pi by 2, then by collecting the complex data, you take the real part and reconstruct the water component. You take the imaginary part and then reconstruct the fat component. It's clear to you guys? Right, so that is one way of actually doing that, and that's been used in cases where field is quite homogeneous. But of course, world is not perfect. You will not have perfectly homogeneous field, so you would have to come up with a slightly complicated ways of imaging fat. In fact, this problem is, even though it appears so simple in terms of the expressions, there are so many, of course, practical complicating factors that it is still an open challenge, and this was actually one of the challenges posed in, I think, 1 year ago or 2 years ago in ISMRM, to come up with, so that people will come up with, this was a competition and people will come up with submitted proposals to be the best way to solve this problem completely without any, in the practical scenario. And I think, well, you can go to ISMRM website and see what proposal won and then what method ultimately was used. But it's, well, actually I don't remember what proposal won, but you can go back and check the website. So this is a small video. I hope it works. Okay. So the right side is the phase image. Left side is the magnitude image. Acquired at different TEs. Of course, this is for, so before we move ahead, this is the image of a leg of a human being, and this is the bone which contains the bone marrow. This is your subcutaneous fat and, well, interstitial fat as well, and that's your muscle. And as you can see, as you move along the TE axis, Why is that not? It is? Okay, I couldn't see it here. Okay, so as you can see, now this is in phase, but you can see that is out of phase. Actually, these two are kind of out of sync with each other in terms of the correspondence, but you can see that when it becomes in phase, this one, you will see not much of a signal loss in these regions and in these boundary regions where you would have fat and water mixed. Let me start that video again. Sorry? Oh yeah, you're right. Okay. I hope this one works. No, second time it doesn't give me the option. I don't know. Okay. So observe the magnitude first. So now you're in phase. Now you're going out of phase where you see these things darkening because of the signal loss. And then because of the increasing T, you have the T2 star decay as well. So that's why you see this bone increasingly becoming darker. But now as we move along, let's go back to this. So if you see this one, so now you're in phase, and then now you're going out of phase again. So the phase of water and fat goes through these cycles. And if in a tissue where you have both, then you would have you see these signal cancellation effects. Is that clear to you guys? Okay. So that's just an illustration. So if you go back to the data and then measure the signal amplitude in fat and water, or in a voxel which contains both fat and water, then you would see this kind of oscillatory behavior within that voxel, and this is your T2 decay overriding it. So that's what you saw in the previous video. You had the T2 decay as well as your cyclic behavior of the vector addition and subtraction as you go through as the phase evolves as a function of time. So this is T as a function of T. I mean, ideally you do your experiment with a given T. So all of these concepts that we're going through is for you to be able to choose the optimal TE, provided you know all these phenomena that's going on in the background. So that allows you to design your optimal experiment so that fat doesn't interfere with the signal that you want to measure, or with the effect that you want to measure. Okay. On the right side that you see is basically the again magnitude signal in pure fat, which also contains a little bit of water, and then you have in water, which is pure water, you will see that there is no oscillatory behavior. In bone marrow, which also contains fat and water, but the fat fraction is higher than water, so the amplitude of this oscillation is not huge because the fat fraction is quite high and the water fraction is small. So even though so it's like this, so even if this rotates, the amplitude is not going to be affected much. So you will see the amplitude oscillation slower. But if this is on this order, then this would be, the amplitude of oscillation will be higher of the signal, I mean. Okay, so now if you want to, if you do your, let's go back. So we just said, yeah, I guess we didn't go over that. So if you have, if you choose your TE to be pi by, so such that this is pi by 2, then with one experiment, with one acquisition, you can get water and fat images. Correct? With just one acquisition. If you time your TE to be pi by 2, and assuming you have absolutely perfectly homogeneous field. Now, like I said, usually that's not the case, but the other way to be able to do this is you choose your TE such that it's either pi, I mean once it's pi, so that's rho water plus rho fat, and then the next time it's pi by, sorry, once it's 2 pi, and then the other instance it is pi, so that it's rho water minus rho fat. So basically in phase would be rho water plus rho fat, and then out of phase would be rho water minus rho fat. So, but if you observe, that's actually two different TEs. So those would be two different TEs, isn't it? Right? TE in phase and TE opposite phase would be two different TEs. So that means that you would have T2 star effects also playing a role here, meaning the T2 star effects in the in phase versus out of phase would be different. So to avoid to overcome that problem, what you could do is, so essentially what we're saying is you either you acquire one data set here or one data set here, and you can also acquire another data set here. So the problem is basically this difference. The T2 this amplitude is your oscillatory behavior is due to the oscillatory behavior, this change, whereas from here to here, this point, the slight decay that you see is due to the T2 star decay or T2 decay in this case. Okay, I think I should try to write here. So this is what you have. Okay. Well, not so wide, but okay. This is in phase, this is out of phase, correct? So at the in phase point, your signal amplitude was this, and at the out of phase point, your signal amplitude was rho prime, which is basically rho times e power minus Te in minus Te out, or Te out minus Te in. Right, that's the amplitude difference, not the phase difference. So the phase, if you ignore this part, by T2 star, by T2. So this difference, everybody follow me on that? See, if you, okay, let's go back. This and this is occurring at two different T's. Correct? So you cannot just use rho water plus rho fat and then rho water minus rho fat and then do an algebraic summation and then solve for rho fat and rho fat. You can't do that. That's because this is a T in, which is different from this one, which is a T out. So there is that delta Te that is affecting your rho, because that's rho times e power minus delta Te divided by T2 star. That's going to affect your signal amplitude. So you won't get, by doing this, you will not get the rho water fraction, rho fat fraction. So that's the point I was trying to make. So the way to solve that is essentially, if you acquire another in phase image and then average these two, then you would end up approximately estimating what is the amplitude here. But then you will use the phase image here. Understood? Then do the subtraction, and then you would get you'll be kind of satisfying that condition. Okay, that's the point. That's what's called. That's also called 2-point method. Sorry, this is 3-point method, where you are assuming that there is no field homogeneity. It's just that T2 effect. Now the chemical shift difference between water and fat, you can use that to actually selectively invert or select. So selectively do either fat imaging or water imaging. Again, assuming that the field is perfectly homogeneous, then the resonance frequency of fat is going to be shifted by 3.35 ppm times B naught times omega, times gamma. So if you can apply RF pulse which is centered at that particular frequency with a very fine bandwidth, which takes into account whatever spread of resonance frequencies that fat would have without interfering with the water resonance frequency, meaning without crossing over the water resonance frequency, and apply that first. Apply an 80-degree pulse so that you tip the fat first and then dephase it completely. Then you apply your alpha pulse, continue with your imaging experiment. Then essentially the fat signal is already suppressed because you already excited it and then suppressed it by dephasing it. So it would not interfere with your imaging experiment. So that's one way of suppressing fat. This is called fat suppression pulse, which people use in typical imaging experiments today so that fat does not interfere with your imaging. For example, if you want to avoid any fat shifts, typically in EPI experiments or even in general imaging experiments where you would expect fat shift is going to cause a problem, then especially around the skull, some people have a lot of it, some people have some, but definitely there's always some fat around your skull, right? So that can actually cause, and the marrow within your skull, there is some marrow within your skull as well. So that can cause some artifacts in some imaging applications, which can be avoided using the fat suppression pulse. So that's basically long RF pulses with very, very narrow bandwidth. So that's fat selective to excite. May also excite water due to field inhomogeneities or too small a fat frequency, basically bandwidth of the fat pulse at low frequencies. For example, that shift in 3.35 ppm is not going to cause a huge shift at, let's say, 1 Tesla, which is at 42 megahertz, whereas it's going to cause quite a bit of wide bandwidth, shift at 7 Tesla or 3 Tesla, and the spread of frequencies would also be proportionally scaled for the bandwidth of your RF pulse that you are using to excite and null the fat signal. So if you have any inhomogeneities, then that is going to be a problem for such a suppression of fat. So that's your fat suppression pulse. This is your spoiling pulse or the saturation pulse, and then you have your normal imaging slice, gradient and RF pulses for your imaging. So the other one that we mentioned earlier in our discussion and is basically by using the T1 property of fat, so that you can null fat tissue signal, and that you saw the example images in the previous lectures. And the third way of actually selecting fat or suppressing fat would be to use the chemical shift property again, but in this case using the phase information like we talked about here. So you can actually get phase water images versus fat image using those methods, where singular co-complex separation is what we talked about, where TE is chosen such that your phase is pi by 2, so that the real part would be water and then imaginary part would be fat. 3-point Dixon method is, 3-point method is this, but it's not particularly a Dixon method. Basically, here we used two combinations, right? One is 0 and pi, the phase distributions of the fat relative to water, but you can use an additional phase term as well to be able to estimate what the background field inhomogeneities are going to be. You can estimate that and then correct for it using third acquisition. So, and multiple acquisitions like that, you can imagine you are essentially, sorry about that, but you're essentially kind of tracing that curve, that is just the magnitude. There will be the phase curve as well, and you're basically trying to use that multiple regression to tease out water and fat images. So again, this is the same thing. So that's fat is 90 degrees. This is 180 degrees. That is 0 degrees. In phase, as long as the bandwidth is same for all these experiments, then the fat shift is not going to change. So you can always, when you create a fat image or a water image, you will always be creating that shifted image of fat. So just remember that aspect, that you will always be, fat has already shifted. This is a function of your bandwidth. It's nothing to do with your phase. Fat will always shift. Now, if you want to kind of minimize that shift, you can increase your bandwidth and then have fat stay within the voxel as much as possible, or to a large extent, I mean. But when you do the fat imaging or water imaging, then you have to consider that you're quantifying your fat in the shifted location, not in the original location. Is that clear to you guys? Okay. I mean, that stems from that equation basically. So, like I said, you can actually predetermine both how many voxels fat would shift, as well as what would be the in phase and out of phase relative to water for fat, because that's just based on the sigma b naught times gamma times Te, where all of these are constants except for Te, which is an imaging parameter that you can change, that you have control over. So at what Te would the phase of fat would be opposed or in phase with respect to water can be predetermined, and that you can use in your experiment appropriately depending on what is your criteria. So as you can see, the separation between two opposed phase here is almost 4 milliseconds, whereas here it's only about 2.5 milliseconds or 2.6 milliseconds, right? So it takes, the higher the field strength, the closer the in phase out of phase options are. In phase and out of phase T's are as a function of field strength. Now to be able to do water and fat imaging, we just said that you can you can use any of these, and the longer the TE you would use, the more T2 star effects you would end up with, correct? So to be able to do experiments with shorter TEs, and remember this is basically related to your phase, not particularly your T2 or T2 star effects. Now, meaning that if you're using longer, let's say you're using a grain echo where your minimum T is only 10 milliseconds, so you have to use T's for your experiment. Let's say you want to characterize water and fat, you would use in phase and out of phase, so that would be 11 and 14 milliseconds. The T2 star decay might be pretty bad here. That would increase your noise basically, meaning it will decrease your signal. The noise is the same, so obviously your SNR is going to go down, correct? So to avoid that, you can do a spin echo experiment with shorter T's, and of course spin echo has larger amplitude signal compared to your gradient echo, and you can use a much shorter TE, effective TEs for getting your phase. So the way you do that is basically, so normally you have your pi by 2 and then pi, and your signal acquisition would be at, this is tau, this is 2 tau, and this is your signal acquisition window. So the phase at the center of the K space would be 0, and you would get this. That phase is 0 both due to your imaging gradients and your chemical shift. We are assuming that those are the only two that are there in your sample right now. So the phase would be 0 both due to your imaging gradients and your chemical shift here in this case. Now let's say you shift your pi pulse slightly to the left, which means that your center of your spin echo is going to be somewhere here, which means that this center of the echo is only going to rephase I mean, none of these has changed. None of these gradients have changed, except for the fact that this pi pulse has shifted left. So here your gradient echo and your spin echo was coinciding. We talked about this at some point in the earlier classes. Because it's coinciding, I mean, the fact that it's coinciding is advantageous, and then there is no phase because of that. Now, whereas in this case, because you're shifting the pi pulse, your spin echo is going to occur here, where the phase due to any other background field in homogeneities or chemical shift. Now we assume that there is no background field in homogeneity, but we just have your chemical shift. So any phase due to your chemical shift is going to be 0 here, not at the center of the echo. Okay, so the center of the gradient echo is what I'm talking about. This is your spin echo. This is your center of the spin echo, whereas this is your center of your gradient echo. That's right. So essentially, because of that shift, you will reconstruct an image which would have a finite phase. Now, because the phase here is 0 due to your chemical shift, but as you move along, there is this 2 epsilon duration from here to here. So during this 2 epsilon duration, you will the chemical shift dependent phase would accrue. So your effective TE for your chemical shift phase is going to be just that 2 epsilon. Is that clear? Everybody followed on that? So all you're doing here is that you're shifting your spin echo relative to your echo, relative to your imaging gradient echo. Okay, so your spin echo would occur here, where phase due to your chemical shift effects is 0, but then from here to here, this phase would evolve, and you would have finite phase due to your chemical shift at the center of K space. So that means your effective TE that for your phase term is going to be 2 epsilon. The advantage of running this is that now you can actually control what 2 epsilon is very minutely, right? So your 2 epsilon can be as short as possible. So effective TE can be as short as possible. So this is sort of summarizing all these 2-point, 3-point and multi-point methods. We didn't go through the multi-point methods in this lecture, but essentially, like I said, it's basically regression along the multiple points, both along the phase and magnitude information. Well, there are something called spatial spectral pulses that you can actually use. Well, I'm not quite. I think we should skip this part. I'm not quite sure about how to explain that part. So, but that's not there in the textbook anyway. So I think that's the end of today's class. Next class would be Dr. Yun-Chan Ye, who would start in chapter 18. Start with chapter 18, and then I think after that, at the end is where Charbel is teaching, right?
I don't know if he's going to anymore. He's going to be traveling. Right?
I see. Okay. So mostly then Yung-Chan, Dr. Ye would be teaching that. Okay. Thank you.